This is a video to show you how to get the Aerocontrols Toolbox running from Jim Sorenson, one of my former graduate students. Has some great M-files functions that will be very useful in our class. Anyway, this Aerocontrols All M-Files 2006 folder contains all the files you need. There's some instructions here in the PDF files. And there's a zipped version which contains them all and which I've put at the PolyLearn site. And the unzipped Aerocontrols themselves contain all of these M-files with embedded instructions again onto how to use them. You run this by running the Aero M-file. And then just listen to the instructions or follow the instructions that come on your MATLAB. So you'll want to set your set path so that you can pick up these files. That's the first. And then you simply have to type Aero in the command window, like so. And here is the M file shown on the right, written by Sorenson. So you can look at it and see some of the things some of the functions that it does give you. We'll just cover some of the basic ones here today. So you'll get the notice on how to get help by just typing help Aero controls if you don't want to go through the documentation. And then you will receive all these of these commands onto how to set things up. We're going to use the shorthand command. That's a good one. And the transfer, this is the time constant form of the transfer function. Notice also you can create lead and lag compensators and PID easily. The other one that we're going to use today is called asymptotic. Let's see if I can find that here. Well, here I've typed help asymptotic. And it says this function creates a Bode plot with the asymptote Bode approximations added. The command is asymptotic. So let's see how this might work. Here I've started a transfer function g equals 25 over s plus 25. And notice if I use the shorthand notation, for shorthand notation g, that anything in parentheses assumes that that's a pole at 25. So this is shorthand notation for 25 over s plus 25. So let's jump right in to this asymptotic g and see what happens. We look over here and we can see from the figure that this thing gives us asymptotic approximation to the Bode plot. The Bode plot, the actual Bode plot, is blue, and the asymptotic approximation is red, both for the gain and for the phase. As a side, you might ask what this Bode plot says. Well, this is an actuator Bode plot, and it says that if I put this into any kind of a control system, the 0 dB means that when I added this Bode plot to my other Bode plots, it would do nothing below the break frequency of 25, or little below the break frequency of 25. There is some small decay from like 10 to 25, but that's 3 dB. So you can see the break frequency tells us where the actuator effectively passes all the low frequency information in our control system. After the break frequency, then, the actuator is going to start attenuating. If you add this Bode plot to all the other things that might be in your system, you'll start attenuating this system. So to show you an application, here I've redefined g after I put the hold onto the plot to be 5 over s plus 5. Now the time constant of this is going to be much slower, so let's take a look and see how the figure came out. Well, here we see our original plot is on the top, and our second plot has a break frequency at 5, and now you can immediately see the effect for the brake frequency, which is lower, you are going to start decaying anything in the system at a brake frequency of 5, which is much slower than the original 25 over s plus 25. Below 5, this system will look just like the 5 over s plus 5 will look just like the 25 over s plus 25 at lower frequencies. But here between 5 and 25, you see there's going to be a considerable decay in the Bode plot, and a decay in the phase angles as well. So in other words, this phase angle of the 25 over s plus 25, so you can see that the fast actuator, 25 over s plus 25, is much better for the control system if you don't want the actuator to degrade the phase of the overall system, or the gain of the overall system. And that's normally what you want. So the faster the actuator, the more expensive the actuator, and we say the higher bandwidth the actuator. All right, you should get this should be able to do your Lab 1 project now. Do your Lab 1 project and try to get the Aerocontrols working.